Good afternoon, everyone. Can you hear me? Bhakti ma'am, can you hear me?
Ma'am, we can hear you, ma'am.
Yes.
Okay, I hope I'm audible here. So shall we start with the session now? I hope many of the participants have joined with us. I welcome all the participants for the post-lunch session. I also welcome our speaker for this current session, Dr. Lalit Singh. Uh, a brief introduction about Dr. Lalit Kumar Singh. Dr. Lalit Kumar Singh received his PhD degree from Indian Institute of Technology from Banaras Hindu University. He is currently a scientist in NPCL BARC Department of Atomic Energy, Government of India since last 20 years. His assignments over the years range from design, development, testing, related research, and site validation of the safety critical computer systems of Indian nuclear power plants. He has published several research papers in journals of high impact factor like IEEE Transactions, IEEE Computer and ACM, and there are many more to add to it. He is also the recipient of many awards like Publication Award, Group Achievement Award, etc. He is also a reviewer of several SCI indexed journals having high impact factor. He is in the panel of Faculty Assessment Committee for Department of CSE in IIT Roorkee to access their research profile and give the recommendations. He is an expert member of Industrial Policy Formation of IIT Ropar, BOS of many autonomous institutes, and member on the advisory board of many institutes or universities. He is a reviewer and project collaborator of research proposals of Board of Research in Nuclear Sciences. He is also the faculty of Nuclear Training Center, Department of Atomic Energy, Government of India. He is interfacing with the other countries like Russia, USA, France, etc. for importing nuclear reactors that are based on new technologies. So far, he has completed 33 projects of Department of Atomic Energy, Government of India. He holds 620 rank in India in the list of world scientists released by AD Scientific Index. There are many more to add to it, but cutting it short and let's start with the session. I request Dr. Lalit Kumar Singh to please start the session.
Thank you, madam, for introduction. Am I audible to all?
Yes, sir.
Yeah, thank you, ma'am. And I'll also like to thank the organizing committee members who has given me this opportunity to share some of the industrial experience to all the participants. So I'll be talking on design thinking for safety analysis of safety critical systems. So before we start, let us try to understand the topic about the topic. Then we can draw a motivation like by understanding the essentiality of the topic.
Sir,
So
sorry to interrupt.
yeah,
Uh, can you please put it in the full screen mode, the
madam,
presentation? Can you
I
please
have
put it in the full screen mode?
I have put in the full screen only. Let me then first stop sharing and that let me start again. Madam, now it is coming in the full screen.
It's okay, sir. ठीक है.
Okay, it is coming on full screen, no? And the slides are changing also.
Slides I can't see changing, sir.
It is
We
not
are on the
changing.
first slide. We are on the first slide.
Let me then share my entire window rather than this particular slide. Just a moment. Madam, can you
Yes,
tell
ma'am.
me now
Yes,
the slides
yes.
are changing?
Yes, now it is going on fine, sir.
Yeah, yeah. Thank you, madam. So, let me discuss about the topic. So first, let us try to understand the safety critical systems. What are the safety critical systems? So these are the systems, the failure of which can lead to the catastrophic disasters, or even it can lead to the loss of human life. And there are a wide range of applications where we use such kind of systems that, include aerospace, medical domain, nuclear energy, defense, automobiles, and so on. Where the failure of this application can lead to very severe consequences, and hence it is very important to perform the safety analysis of such systems. So I'll be uh, discussing how we can make the use of the design thinking for performing the safety analysis of such kind of systems. So the today's outline is first I will introduce about the safety background, and then I'll be introducing a mathematical modeling technique known as PatriNet, which I'll be using to model my system and how I can, derive the safety aspects from that system, how I can evaluate the safety aspect from that, model. So I'll be taking a real case study and then I will perform the safety analysis and then we can conclude the session. So now we all know like a computer has become an integral part of almost all kind of systems, whether those are real-time systems, the control systems, the safety systems, and it is all being used almost in all the domains. And because the dependability requirements that includes the reliability, the safety, the performability of such systems are very high, especially if you are dealing with the safety critical systems. And so to evaluate the safety aspect, it is very important to stress the system so that I can find out like under this such stressed conditions, what would be the behavior of my system. And we all know like these systems are not the standalone software systems or the standalone hardware systems, but it comprises the hardware as well as the software components. And we know like software does not harm anyone, but only the hardware that can harm, but ultimately the hardware is being controlled by the software, and hence the software safety must be considered as a part of overall system safety. And the disasters are often the result of multiple failure sequences which involve the hardware or the software or the human failure. So our main objective would be like how this the PatriNet model can assist in designing and analyzing such safety properties or that is related to the fault tolerance or multiple failures. And so let us first understand the history of the PatriNet. So when I talk about the PatriNet, as I said, it is a very good graphical and mathematical tool. Why graphical tool? Because I'm able to simulate my system in a graphical form where I can run that particular system, and I can gain enough confidence what could be the system behavior when it will be running, when it will be deployed in the real time. And why it is a mathematical tool? Because we can make the use of the mathematical knowledge. We can embed that mathematical knowledge in the PatriNet, and we can come out with some kind of critical metrics. We can evaluate some critical metrics using mathematics, and that will be the indicators of the safety. So it is the best communication between the theoreticians and the practitioners. So if you look into the history of PatriNet, the concept was introduced by a German PhD scholar known as C.A. Patry in his dissertation in 1962. And he introduced this concept basically to model the stochastic processes. So if I want to categorize the processes, the types of the processes, I can do it into two ways. One is the stochastic process, and the other one is the deterministic process. So the deterministic processes are those processes, the outcome of which can be 100% guaranteed. For example, if suppose I do have a pen in my hand, and if it gets slipped down, I can 100% guarantee it is going to fall down on the earth because of the gravitational force that is acting on the earth. And hence I can say it is deterministic in nature. But there are many processes, the outcome of which cannot be 100% guaranteed in spite of the rigorous planning or the systematic approach. And such processes are the stochastic processes. For example, suppose you do have the flight from Mumbai to Hyderabad. Then there may be, you probably use the normal route from, your home to the airport. But then also you may miss your target in spite of the rigorous planning and considering all the traffic delays, some extra amount of overhead, and the reasons could be manifold. The reasons could be probably the normal route is under construction, and you came to know when you were about to reach the airport just half kilometer before, and you have to take a U-turn, and then the route is excessively longer than the normal route, as well as all the traffic might have diverted to that route, which further may delay your your arrival to the airport. So I mean to say, there could be, when you reach the airport, you may find there is excessive flight delay, or the flight got cancelled because of some technical or administrative reason. So what I mean to say, in spite of rigorous planning, it may happen like you may miss your target, and such processes are stochastic in nature, or known as stochastic processes. And even if you talk about the human is also not deterministic in nature. He keeps on, changing his mood because of the dynamic scenarios, and hence all the systems that are made or developed by the human will definitely be a stochastic process. In this 19th, after going through the thesis, the people really appreciated, and they were, because there was an era where the people were working on the concurrent and parallel systems. So with this objective, MIT USA conducted a conference on concurrent system and parallel computation to explore whether such modeling construct can be used to model such kind of parallel computations or concurrent systems. And the conclusions were very fruitful, and the people were more eager to strengthen the model, the capacity of the model to solve more and more complex problems. And with this objective, again, they decided to meet in 1975 in a conference on Petri nets and related methods. And then the industry also started using it, and looking at the industrial demand, a course on general net theory and processes and systems were introduced in Germany. And thereafter, it got a popularity, and the people from different domain also try to explore whether this modeling construct can be used for their particular domains. And with this objective, the first European workshop on applications and theory of petriness were conducted in France in 1980. And then the researchers were coming out with a different flavor of petrinets. For example, if I want to work on the real-time system, definitely there must be a provision where I can embed the timing information. And for that, like a specialized Petrinet known as time Petrinet has been, evolved. So the first international workshop on time Petriness was conducted by Italy in 1985. So there are other flavors of the Petrinet also, depending on your particular application and the interest. So although this is not an exhaustive list, but it gives some of the important milestone, which shows the importance of the patronets, and it also shows the how it became popular through like in the industries. So if you look about the battery networking mechanism, so suppose I'm taking a very small example. Suppose I want to model a very small chemical reaction, that is 2H2 plus O2 that gives 2H2O. And before going to the modeling, I want to introduce the basic building blocks of the patronets, along with the, its their roles and functions. So if you look, there are the three big circles in this figure. So this is a basically patronet figure. In this, there are the three big circles, and each circle is known as place. So there are the three places, and I'm using these three places to represent the hydrogen, oxygen, and water. And then there is a rectangular bar, which is representing the transition. And the places can be connected with the transitions, and the transitions can be connected with the places with the help of the directed arc. And then there are small embedded circles in the places, and these embedded circles are known as tokens. So for example, hydrogen place contains two tokens, and I'm representing this token to represent the number of atoms in the hydrogen. Similarly, oxygen also contains two tokens, and hence I have put two tokens over here. And so as these places are connected with the transitions with the help of the directed arc, and these arcs do have weight. For example, the arc that is connecting hydrogen place in transition T is having weight 2. And the arc that is connecting oxygen place in transition T is having weight 1. So if I don't put any weight, by default it is treated as weight 1. Similarly, the weight of the arc that is connecting transition T, and water is weight 2. And then there is a concept of input places and output places. So I'll be telling the significance of this weight shortly. But before that, there's a concept of input places and output places, and input transitions and output transitions. So the places which are connected from the input arcs are known as input places, and the input arc for an entity is that arc whose head is on that entity, is terminating on that particular entity, and the tail is coming from somewhere else. And the output arc is of any entity. Entity means place or transition. Will be, it will start from that particular entity, so that the tail will be on that particular entity. So here you can say, for the hydrogen place, there is only one output arc, which is connecting to T. Oxygen place also having one output arc, and hydrogen place is having one input arc. Similarly, the transition T has two input arcs and one output arc. And now this one interesting fact is the distribution of the tokens among the places represent the state of the system. I repeat, that is very important. The distribution of the token among the places represent the state of the system. So for example, here the distribution of the token is 2, 2, 0, because hydrogen place contains 2 tokens, oxygen place contains 2 tokens, and water place contains 0 token. And this is the state of this complete process. And this figure represents the left side of this chemical equation, that is 2H2 plus O2. And now it has to be converted into the water. So it means I need to change the state of that particular system, because here ultimately now it is changing the state. And as I said, the state is represented by the distribution of the token. So definitely I need to change the distribution of the token. But there is a law by which the distribution of the tokens can be changed. And the law says that at least one transition in the Patrinet figure must be in enabled state. So because this Patrinet figure contains only one transition T, so this T must be in enabled state. And what is the criteria of the enablement of the transition? The criteria is all its input places must contain sufficient number of tokens. So for example, in case of this transition T, the input places are hydrogen and oxygen, and these two places must contain sufficient number of tokens. But who will decide the sufficiency of the token? What is the sufficiency criteria? So that will be totally governed by the weight of the respective arc. For example, the weight of the arc connecting hydrogen place and transition T is 2. So hydrogen place must contain at least 2 number of tokens. Similarly, the weight of the arc connecting oxygen place and transition T is 1. So this oxygen place must contain at least 1 number of tokens. So this criteria fulfills here. So it means the transition is in enabled state. And when it is in enabled state, it can fire. And after firing, the token can move from input places and to output places. But how many token can be moved out from the input place and how many can be deposited into the output place? That again will be governed by the token. So that again will be governed by the weight of the respective arcs. So here the weight of the arc connecting hydrogen place in transition T2, and the weight of the arc connecting oxygen place and transition T is 1. So after firing transition T, the two tokens will be moved out from the hydrogen place and one token will be moved out from the oxygen place. And then, so it has become now two tokens has been moved out from the hydrogen place and one token has been moved out from the oxygen place. But how many will be deposited in the output place? So that again will be governed by the weight of the output arc. And the weight of the output arc is 2. So only two tokens will be deposited in water place. So one important conclusion that we can draw here is there is no law of conservation of token, because we have seen although three tokens have been moved out, if you consider the sum of the token of from all the input places, but only two tokens gets deposited in the water place. And now the state has become 0, 1, 2, because as I said, the state is represented by the distribution of the tokens, and now the distribution is hydrogen place contains 0 token, oxygen contains 1 token, and water contains 2 tokens. So 0, 1, 2. And now you can again validate the enabling condition of the transition. So now it is not an enabled condition. Why? Because all the input places must contain sufficient number of tokens. So here you can see although the oxygen is containing sufficient number of tokens, but hydrogen is not containing. So now it is not an enabled state. And now so you can see like it is a dead state. Now it cannot change that state. And I want to introduce one term known as the reachability graph. As I said, it is a graph. So all the nodes will be representing the state of the particular system. So it means it is representing the token distribution, and the arcs will represent the transition which is responsible to change the state. For example, in the reachability graph, the first node will contain 220. So 220 is one state, and then after t, it will become 012, and then it will be a dead state. So now let us consider a case study known as the reactor protection system or the shutdown system. So this is a typical uh, pictorial representation of the system, and where you can see, let me first explain the working mechanism of this system so that then you will be able to model the system. So if you are able to see in the right side, there is a big sphere, and it is known as the calandria, where the nuclear reactions are taking place. And we know like when the nuclear reaction takes place, it releases much heat energy. So here a lot of heat energy gets created, and nuclear fission reaction is basically a chain reaction, and which is sustained because of in every reaction the neutron gets generated, and again this neutron will be utilized to further for to generate a new chain reaction. So the neutron population keeps on increasing, and in every reaction a large amount of thermal energy also gets created, that is 220 million electron volt of energy. And so in case of because as we have come to know, this neutron is very important, and it is only responsible to increase that it is also responsible for the chain reaction. So it is very much important to control the neutron population. So otherwise, what happens? If more number of neutrons will be created, the more heat will be generated, and this can jeopardize the integrity of all the constituent components, right? So it may start melt, or the fuel may start fail. And then in case, so basically, to control the neutron population, the control systems are designed. But in case of the failure of the control system, if in case it is not able to control the parameter, the critical parameters, we have to just shut down the reactors. Shut down the reactor means we have to kill all the neutrons that are generated here, and for which this system is responsible. So what happened? You can see from the calendria, there are the tube which contains so many pores, and from that pore, some poison gets injected, which can eat up all the neutrons. And this tube you can see is extended. If you can backtrack, and it is connected to the poison tank. And in the poison tank, basically the poison, there is a liquid which gets filled. Why it is poison? Because it can kill all the neutron. And in the top portion, a floating ball is placed for the smooth injection of this poison into the calendria. And now it is connected with some set of walls. You can see there is some set of horizontal and vertical wall, and which is connected to the helium supply tank. Now, why helium supply tank? Because it can create a pressure, and it can pressurize, and that pressure can be passed through these lines, and it can pressurize the floating ball, which can inject the poison into this calendria. But let us see, like, what is the role of these many walls which we are able to see in horizontal and vertical. So by default, when your system or when your reactor is under normal operation, this horizontal wall is generally closed and vertical wall is open. Now just try to analyze, if there could be only one valve, our life would have been simple. For example, if I want to take the water, I am opening the valve. If I want to close the water, I am just closing the valve. So in case if I would have only one valve, normally it would have been in the closed position, and when there will be the requirement of poison, I can open so that the helium pressure can pass through, and it can pressurize the floating ball, and which can pressurize the poison into the calendria. But what could be the wrong with only one valve? Suppose if it fails to open because of some mechanical failure, then we will not be able to shut down our reactor, and it can lead to the catastrophic disasters. So for that, I can I can put one additional valve parallel to this valve, so that if one fail to open, the other can work, and in this way I could serve my purpose. Then what? Then okay, fine. Then only two valves are required. then what is the need of for the rest of the valves? Now suppose you consider a case that after, because of this, when there was a demand to shut down the reactor, I have opened the valve and the poison got injected, and now I want to restart my reactor after doing maintenance. And for restarting, again, I have to close this valve first. But what happens if from the two parallel valve, if anyone fail to close, anyone, then we will not be, uh, you know, uh, will not be able to stop the helium pressure, and the pressure can go through this line. And hence, it is required to put one additional wall in each parallel line so that it can take care the failure mode valve fail to close when I really want to restart the reactor. Okay, then I could understand like, okay, four walls are necessary, but then what is the need of these two walls which are vertical? So the why it is required? Because suppose there is a leak in one wall, first wall. So what will happen? The pressure can develop in that particular line, and it can try to jeopardize the integrity of the second valve. And to avoid this situation, we have to release the pressure. And to release the pressure, this vertical, you know, uh, valve is used. And hence, we have to put this ventilation or vent valve in each the line. So these valves are known as vent valves. And these four valves are known as quick opening valve because we have to quickly open the valve as and when the demand to shut down the reactor comes in. So this is, you can see like these helium tank, calandria, poison tank, all are static elements. Only these are the dynamic elements. That is the closing and opening of the valve. So let us, these really play a very important role with respect to the safety. So let us try to model this, the operation, operating mode of these valves with the help of the battery net. So this is a battery net model. Let me explain this. So suppose the PPD place, it represents that any trip parameter has deviated, or it means there is some demand to shut down the reactor. And this is coming from by reading the trip parameter, reading the values of the trip parameter. So here there is one, token, which basically represent that there is a parameter trip. The trip parameter is deviating, and then we have to send the signal to energize the relays to close the vent valves, and we have to, create some logic condition also. So logic condition in the sense, suppose you, when any road construction goes on, you put a flag so that any passenger that comes in will come to know, okay, I need to take some alternative path. So the TPD transition represents that the signal has been sent to create the logic condition as well as to energize the relays to close the vent valves. And then if the token comes in PLC on, it means logic condition gets created. Then after that, TLCH is represents the transitions that it is on hold state. This logic condition is on hold state. So when I put a flag, I keep on hold till I complete my construction work. So PLCH represent that the logic condition is in hold state. And now see the vertical, uh, the token will also come in PREVV, which represent that relays have energized to close the vent valves. So what happens before that? Coming back to this, figure, you see, whenever there will be demand, we have to uh, first see by default when your system is on normal phase, all these four valves are in closed state and all these two vent valves are in open state. And when there is a demand to shut down the reactor, suddenly, first, we have to close the vent valves. So the logic is written that first the vent valve will close and then the quick opening valve will be opened so that the pressure can be go inside. Otherwise, if I would have opened the quick opening valve first before closing the vent valve, all the pressure might have released to the vent valve. And in case of restart the reactor, you have to do the reverse action. So here, the first thing is we have to close the vent valves, and PREVV is a relay that energizes to close the vent valves. And TVVC is the trigger to close the vent valve. And if the vent valve is closed, the token will be deposited in the PVVC. And then we have to open the fast acting valve. So the TFAVO represents a trigger to open all the fast acting valve. And then it will open, the fast acting valve will be opened, which can be analyzed by looking at the token in the PFAVO. And now, once it has been done, uh, you one more interlock we need to put in. Before opening the fast acting valve, we have to check whether the fast acting valve is already not in closed state, which which can be checked by the token in the PFABCO. And if it is not, then only the token can be pulled in PFABO. And then we have to, after that, if suppose the logic condition goes off, it means I have to restart my reactor. Then the first thing is the token will be PRDVV. It means we have to open the vent valves first. So the relay will be de-energized to open the vent valve, which can be shown by putting a token in PRDVV. Then it will be TVVO is a trigger to open the vent valve, and PVVO is basically represent that the vent valve gets opened. So this way, this entire system has been modeled, but the two places that I have missed out are very important. One is PFAVCD and one is PFAVOD. These are the redundant information about the closing and opening state of the fast acting valve, which is important. So I'm getting this data from the different sensor. Right? So in this way, and interestingly, all the weight of all the transitions are one. And now I have to find whether any hazard are there in this model, in this system. So what I will do, the basic idea is, let us try to convert it into the reachability graph, which will give the state diagram. And let us try to find out if any states are risky. And if any states are risky, let us try to avoid it. So what I have done is, This is the reachability graph in which, as I said, the first node will be, uh, as I said, the distribution of the token represents the state. So only the tokens, the states which are containing tokens are PPD, PFABCD, and PFABC. And because these are the potential places which can enable or disable this transition, right? So this is the potential places to enable the transitions. Otherwise, if any place does not have any token, it cannot uh, enable the transition, because the enabling criteria is at least, like, all the input places must contain sufficient number of tokens. So here, in the reachability graph, we can only write PPD, PFABCD, PFAB. We can only write the places which contains the tokens, because that has the potential to change the state. So here we have written PPD, PFABCD, PFABC. And now let us go back and see what is happening. So the transition TPD will be enabled state when, and this token will moved out and will be deposited in PLC on and PREVB. As I said, there is no law of conservation of the token. It all depends. It all governs about the weight of the respective arms. So what is happening here? PPD has been replaced by PLC on and PREVB, and rest of the places are like same. And then we can keep on deducing till we cover all the states. And this is the entire reachability graph that we can construct. And now our main aim is you have to analyze each and every state of this graph. So to see like whether this is not a risky state. So from our analysis, we could find like S3 and S6 are the risky states, which are marked by a solid triangle in the left top of that particular state. And why this is a risky state? First, let us try to analyze S3. So you can see there is a PLCH which represents that logic condition is on hold. PREVV, which is represent that it is energizing to operate the Van Waals relay. And here PFAVCD, it is representing that fast acting valve is closed. So duplicate redundant information and main information both are showing it is closed. So you can see the controversy that in spite of logic condition is on hold, then also the fast acting valve is on closed condition, but it should be in open condition. And hence it is a very risky state. So you have to ignore this state anyhow. Similarly, analyzing the S6 state, there is PLCH, PFABOT, PVVC, PFABC. Now you can see there are the controversial state in PFAVOD and PFABC, because one information is saying that fast acting valve is in open condition and one is saying that it is in closed condition. So whose information is correct? And hence it is a risky state. So let us mark this state. And then in this way we can analyze the rest of the states. And after that, we have to think in what way we can ignore these states. So the idea is very simple. If you can just try to first resolve the case of S3, and this is a risky state as we have identified, and which is coming from the S2 state through the transition TLCH. Now, if you can see from the S2 state, there is one more state which is creating, that is S4 by
ಮೇಲ್
by
ಇಮೇಲ್ ಅಲ್ಲಿ ಬಂದಿದೆ
TVBC.
HOD side.
So you can see, there are the two parallel transitions. There are the two parallel transitions, and one is TLCH and one is TVBC. So you have to, and one is leading to the failure state or risky state. So you have to devise a mechanism such that when these two transitions are in race condition, you have to ensure that only that TVBC wins, so that this transition gets fired and it can lead to the S4 state. So then there will be no possibility at all for the confrontation of S3 state. So you can prioritize the transition when they are in the race conditions. So our problem is solved. How we will do that, we will see later. Similarly, to avoid the S6 state, you can see S6 is coming from the two state, one is S3, one is S4. But we have already resolved the issue so that S3 can be nullified. And hence now we can only consider S4. So it is coming from the S4 state. Now again we can see from the S4 the two states are created, one is S6 and one is S7. And because S6 and through the two transitions, that is TLCH and TFABO. So it means these two transitions are in race condition. And hence again I need to prioritize the transition which is leading to the safe state, that is S7. And this transition is TFAV0. So this is the way we can do that. And similarly, we can, see the other states which are not risky states. And now let us see how we can do that. So we have to first prioritize, going back to the same figure, we have to first prioritize the TVBC. And we have to give the less priority to TLCH. So the idea is very simple. How we can do in the modeling. So if I want to prioritize any transition, I have to, and I have to, give the least priority to the other transition. So what I will do, identify these two transitions and put one place in between and start connecting from the transition which has to be given the high priority. So TVBC has to be given the high priority. Draw a arc which is connecting to the new additional place and connect it to the transition which has to be given the least priority. So in this way we can prioritize the TVC, because to fire the TLCH there should be a token in this additional place I2. Sorry, one is I1 and one is I2. And this can, the token can be deposited here provided that the TVBC has already been fired. And similarly, we have to prioritize the TFABO. So again, one additional, place can be put and which can be connected to the transition which has to be given the least priority. So now my problem is resolved. And what I can do it to validate, again I can draw the reachability graph. And this is the reachability graph by considering both the additional places, that is I1 and I2. And here we can find there is no risky state now. So, but what happened? Did you, the story doesn't, stop here, but because we have to go for the optimization. Engineering is all about the optimization, not only giving the solution, optimized solution. So as you can see, these two additional places, I1 and I2, are just an overhead because it is not performing any function requirement. These are placed to address the safety requirements. So what we can do is, because this will, incur additional computation. So we can see, can it be possible after removing I1 and putting only I2, and then I can draw the reachability graph and I can see whether no risk states are there. And if it is there, okay, then my problem is solved. I can ignore that. If I am not able to see, I can do vice versa. I can put I2, put I1 and ignore I2, and then I can again draw the reachability graph. So after putting I1 and ignoring I2, this is the reachability graph that I got. And again, we are getting the risky state. So again, it is not serving our purpose. And after considering I2, we are, getting the state which is not a risky state. This is what. So it means only we can reduce the one additional, state. Now let us see like how we can uh, implement these things. So to implement, we have to just prioritize the transition, and we know like real-time operating system provides a feature through which we can prioritize the tasks. So therefore, we can, impose a precedence among the, so one, we can use the real-time operating system where we can hardcore, we can prioritize the task. The other way is to impose the precedence among the parallel transition to avoid risk state, is to enforce the firing of transitions as per the defined priority. So you can put a condition that is minimum TLCH is always greater than maximum TFAVO, so that always the TFAVO will be fired and it can be ignored. And this constraint must be checked by the hardware or the software logic as per the requirement. If the system fails to meet this constraint, the logic must be built in the design such that the control reaches back to the originating state of risk state and retry the processing meeting the same constraint. And this logic can be achieved by the soft watchdog or the hard watchdog. And in case of hardwired system or module, hardwired logic must send a periodic pulse to the watchdog. The moment the constraint is given in equation 1 fails, it must stop sending pulse to the watchdog. And the watchdog must maintain the current and its previous state. So whenever the watchdog stops getting the periodic pulse, it will load all the dynamic values of the previous states to ensure the safe state of the system. So the other possibility is we can reset the microprocessor IC through the reset pin, and this will reset the entire system state. And this watchdog can be implemented as a soft watchdog or hard watchdog. Similarly, in the case of software system or module, the software must send a periodic pulse to the watchdog to the process in the same manner as the hardwired system does. So this is all about the implementation, but we have to consider the other aspects also. For example, a logic condition has been created to trip the reactor, and the embedded system then also is forcefully closing the vent. Embedded system is trying to close the vent valve, but some bad signal comes to override this closing logic, and which can be identified by the consistent or inconsistent information in these redundant places, that is FAVO, FAVOD, and FAVC and FAVCD. So there could be a real condition or there could be a fault. So the logic in this case, the logic must be built into the design that in either case, the system will treat that the fast acting valve is in the closed state, and again I have to resend the signal to open it immediately. And this can be done by, we can introduce a new safe transition, TSAVO. This is the safe transition, TSAV, TSFAV. So this is a safe fast acting valve. So when in such case, even if the vent valves are not getting closed, we have to forcefully close, and fast acting valve has to be forcefully open. So it will pull the token from the fast acting valve and it will deposit into the fast acting valve open. And this is how this problem can also be treated. And so you can see like and again, there will be the two parallel transitions, the TSFAB and TFABO. And again, we have to remove the conflict. So it is necessary to impose a constraint which can guarantee the failure detection to wait until some consistent state is allowed. And for that, again, we have to push a similar constraint, that is minimum TSFAB. It will be greater than max TFAB. And now we can again validate the design using the reachability graph of the modified Batchinet model and the resultant. So this is the final model which we could get, and we have addressed some of the issues we have seen, although like initial solution we have found by introducing the two additional places, one is I1 and I2, but we could see like uh, we could able to meet our requirement by only by discarding one additional place that we have done. And we have also considered the security aspect, that if somehow, because these are the distributed systems are distributed in nature, if somehow there is a uh, risk or there is a security threat, all the time we have to ensure like we should be able to open the fast acting valve, and this is a robust model. So definitely I mean robust in the sense the in what way, in the what possible way I can think about. So there is we can look into more deeper aspects for which more deep and analysis is required. And after this creating to this model has been taken as input to create the reachability graph. So this is a reachability graph where you have seen that there is no risky state, and the states which are marked with the solid circle in the left top are just end states. These are not the risky states, and hence we can go for the implementation using the similar concepts. And this is so similarly this analysis can be further investigated for more issues, and definitely it may be a time taking process. Why time taking? Because the system analysis required, the domain knowledge is required, and the modeling knowledge is required. analysis knowledge is required, experience is required. So definitely it may be a time-taking process, but the benefits can outweigh them. Looking from the safety perspective, which is very important with respect to the safety critical systems. So in conclusions, we can see that the analysis can be, if your system is very large, definitely you will have many places and many transitions. So what you can do, you can identify the critical functions and you can emphasize only on those critical functions to address the safety feature. And then you can integrate the entire analysis. So the analysis can be done in parts, maybe component by component, or even function by function, in case the volume or criticality of the function is much. In the similar fashion, the analysis can be done for the component connectors as well, or the interfaces as well. And one important thing is, you should know, like, all the risks do not have equal probability. So the system analyst has to play a critical role, that which risk is higher and which requires further or deeper investigations. So that's all about my talk, and these are some of the references which can be referred. In case of any questions, I'll be happy to answer. Thank you.
Participants, do you have any queries? If you have any queries, please ask. You can post it in the chat box also. Sir, I don't think they have any queries.
Okay.
They have followed everything that was explained.
Okay, that's good. So thank you. Thank you.
Thank you, sir. Thank you, sir, for spending your valuable time with us. Thank you for all the valuable insights that you have shared with us. Yes, Santosh, sir, you want to say something?
No, ma'am. I'll just say thank you, sir,
Uh-huh.
for the whole session, ma'am.
Okay. Sir, there was one query posted.
Okay, let me check.
Uh,
Okay, what is the other second name you have said to the stochastic model? Actually, there are the two type of process. It is a process basically. One is the stochastic process and non-stochastic process, or deterministic process. Okay, so stochastic and deterministic. And stochastic, you can say the probabilistic also. Probabilistic model, because it contains a probability. It is not 100% sure. Okay, or non-deterministic process also you can say. Okay.
I hope, Mr. Venkata, your question is answered. Thank you, sir. Thank you so much for being with us.
Thank you, madam.
Participants, please fill the feedback form. For today's session, this current session. Thank you, everyone. We'll meet tomorrow at 9:30 sharp.